Hi there. Thank you for joining me today. My name is Adi Rozenberg and I'm the CTO and co-founder of VideoFlow. In this session, I'm going to talk about the enhanced usage of the RIST specification to address the network challenges. The Reliable Internet Streaming Transport, also known as RIST, is an open specification. The RIST is a blueprint of the communication and signaling needed to provide a reliable and secure stream across any IP network. This is to assure interoperability between vendors and manufacturers. But the specification also opened the door for innovation, and this will be the focus of this session. I'm going to discuss retransmission throttling, retransmission options, and bonding support as they were designed by VideoFlow in conjunction to the RIST specification. The agenda for today is the following. I'm going to do a short introduction to VideoFlow. What is the problem with ARQ? Why should I care about bonding and torture? Introduction to the use of bonding for deferred protection. And I will finish with some use cases. So what are we looking for when we are doing video over IP? The IP network of any type can be fiber, MPLS, DIA, Open Internet, 4G, 5G, VSAT satellite, has its own unique impairment issues. No one wants to see the tiled picture on the left side. Instead, we want to have the right picture, and we want to deliver that for 24/7 service. How can we achieve that? So let's start with talking about the problem with just ARQ. ARQ, automatic repeat request, only provides retransmissions of packets in response to a loss. This in theory can provide 100% packet recovery, but this is if you have enough buffering and bandwidth. Bandwidth or impairments are not always under our control. So let's consider the situation on the left. We have a nice stream flowing and a link budget. When suddenly the link budget goes down, we have a depression of the bandwidth. So it creates a short interruption and packet loss. Then the bandwidth goes up and the stream comes back. This is where retransmissions kicks in. We can see that in the yellow area, retransmissions start to react to the lost event. But the size of the depression is such that we need to have two areas. We need to have the yellow, which is contained in the link budget, but also the red one, which is the theoretical one, which cannot be sustained because there is no link there. So instead, we will have the right. We will see the retransmission starting, hitting the ceiling, and then it will start force downwards, taking bandwidth, and this will basically also push on the stream and create more packet loss. It will push and push until the link will choke, and that is not what we want. Instead, what we really want is the lower picture. We need to have a throttling, ARQ throttling mechanism to adapt to the link budget, not to interfere with the stream, and allow the stream to continue without any additional impairments. So this is our goal. Let's see how to achieve that. This is where VideoFlow Smart ARQ comes into play. VideoFlow does close monitoring of the link budget and the retransmission requests. Stream packets are prioritized for transmission, while the retransmitted packets are first sorted out based on their timestamp. A closed-loop monitoring system measures the link budget and controls the retransmission, throttles the retransmission to use what is available. Another unique VideoFlow source adaptivity is in use in case the link budget is not sufficient for the stream to pass through, but this is a totally different session that we are not going to touch base on. So VDFlow has 3 different techniques to achieve that. And let's talk about it. First one is retransmission rate limit per stream. This is an allowance of bandwidth for retransmission. The bandwidth is on top of the stream and up to the link budget. Imagine that you have a 15 megabit link budget and a 10 megabit stream. You will allocate 5 megabits for the retransmission. The retransmission may only use that 5 megabits. If it doesn't have that 5 megabits going down, then it will adapt to that, but will not take any budget from the stream itself. Another technique called a full stream rate. This is a joint allowance for the stream rate and retransmissions, and to hit a known ceiling, which is the link budget. So that if the stream and the retransmission go beyond a certain ceiling, it will be cut off. It can cut the first the retransmission, but then it can also touch the stream itself. So if we have a VBR stream that is, let's say, 1 to 16 and the link budget is 15, the ceiling will be hit at 15, so 1 megabit will be dropped off, but then it will be retransmitted. But in this case, we can make a good use of the available bandwidth. If it's a VBR stream, we can make use of the entire bandwidth from retransmission. And if we have null packet deletion, which is a part of the main profile, we can gain more use of that bandwidth for the recovery where needed and as needed. The third technique is the shell protection. Shell protection can be seen here. Just like with the first and second technique, we have an allowance of retransmission. Each stream has its own allowance. So it's an effective usage of the bandwidth. Instead, we can use the protection as a shared resource so that the stream may be pulled retransmission budget from that shared resource, so we can have lower overhead and a reduction of bitrate to 20 to 40% in the link budget, which will make the CFO happy. Now let's turn to the next topic, which is the bonding support, as it is allowed by the RIST Simple Profile. So the theory is very simple. A sender device will use multiple links to deliver a copy of the stream to the RIST receiver. Each link should use a specific RTCP session, and ARQ may be used on any link. The stream may be sent as an original IP and destination port, as those may change as long as the original RIST stream is maintained. This is similar to 70.20.22.7 with an added ARQ for resilience. To allow RIST bonding support, VDFlow has added some support features. So let's talk about them. The sender can maintain the original destination IP and port, which is normal. But then the sender may change the destination IP and port to be of unicast or multicast, regardless of the source. The sender may change also the source IP, which is important for unicast, but also may be used for security concerns. Now, retransmissions. We have 3 retransmissions options. The regular one is a normal stream and retransmission using the same link and path, just like any simple profile will do. But then we have 2 other options. One will be stream only, to be sent over one link, retransmission only to be sent over another link, as long as the receiver can accept both and reassemble that to one stream. I will show this use case later on. Then we have dynamic closure. We allow to stream the full copy of the stream or split the stream between multiple links, where each link carries a subset portion of the original stream based on a ratio. If one link fails, its portion is then taken by its peer links until it comes back. So it provides a dynamical reaction. Of course, we assume that the RIST receiver supports the simple profile section 5.3 and 5.4 specification in regards to retransmissions and bonding. So let's talk about bonding. Let's see an example. In this example, we have 3 links. 2 will use RIST Main Profile tunnel, and 1 link will use a regular simple profile unicast or multicast. In this example, the sender has 3 links, while the receiver has only 2. The sender takes the stream and duplicates it across the 3 links, so that we will see 300% of the stream reaching the receiver. The bonding allows for fast lost packet recovery. Any packet lost on 1 link may be recovered from a duplicate packet coming on another link. Once again, similar to the 2022.7. But if the packet is missing after all, then the ARQ can retransmit over any link, 1 or more links, for assured recovery. Bonding is a great solution for fast recovery at a lower delay. The major penalty is the higher upload and download requirements from the sender and receiver. Sorry for that. Now let's talk about dynamic loader. In this case, we split the stream between multiple links. Each link will carry a portion of the stream based on a fixed ratio or dynamically allocated ratio. In the following example, we split the stream in a ratio of 45% and 45% between ISP-A and ISP-B, and the remaining 10% are sent on ISP-C. The receiver reaggregates the 3 streams portions back to 1 stream, and if any link delays need to be compensated, that is done with the use of the RIST Simple Profile grace time capability to assure proper delivery. Any packet loss after the aggregation may be requested using 1 or more of the links for a full recovery. The main advantages are: A, we use less bandwidth compared to the bonding. In this example, 100% versus 300 in the previous slide. Then we have adaptivity. If 1 link suffers, the others can pick up the slack. Even a full link failure can be handled. So if ISP-A goes down, ISP-B and ISP-C can react to that, pick up that ratio, and when ISP-A comes back, it will go back to the original state. It also provides a simple redundancy scheme that I will show later on. The major disadvantage is that you will need to have a slightly higher buffer to adjust all link delay. To make the loader a reality, it must be coupled with ARQ throttling to optimize the use of each link. Now, VideoFlow has introduced a new concept. We call it deferred protection. Deferred protection allows the use of the RIST Simple Profile specification and provide 3 distinct ways of streaming. As I mentioned before, we have the normal simple RIST where the stream and the ARQ are using the same link. We can have stream only on a specific link, ARQ retransmission only on another link, and any combination of the above 3 options. In this slide, we can see the loader being performed on the stream between ISP-A and ISP-B, both taking 50%, but we do not allow any ARQ to be used on those links. This means a huge and a significant bandwidth saving and, of course, cost. The retransmissions are pushed to ISPC. It is sent over low-cost link and of low capacity because it's only retransmissions. These techniques saves ISP A and B link budget, so no special headroom is needed and thus saving cost. This is perfect for unidirectional streaming solutions like satellite and VSAT, with the recovery conducted over the internet mobile for lower overall delay. So let's see some use cases for that, for bonding and load-share. The first use case shows bitrate bonding across multiple DSL links that may be suffering from first-mile packet loss. The receiver takes the two duplicates and reassembles them as a single stream. Next is a dynamic load-share. In this case, we split the stream to 50-50% between the two ISPs. This can be a regular use case for load-share, but it also is an application for location where you don't have enough link budget on one ISP. You can tie up multiple links so that now you can have a solution to send a higher bitrate using multiple links while splitting the load and portions between them. Next diagram shows a dynamic link backup. In this slide, we see the coupling of DSL and mobile for a load share and redundancy scheme. The main body of the stream is sent over the DSL link. So in this case, 97% are sent over ISPA, while the mobile we are sending 3% over the mobile, so that we'll keep it hot and standby. If from some reason the DSL goes down or has severe interference, those can be picked up by the mobile device, and once again, 100% hits the receiver for clean and pristine video. Now let's talk about deferred protection. We will use the same diagram that we showed before with the mobile and DSL. In this example, we allocate 100% of the stream without protection to the DSL. And for the ARQ, we use the mobile link, so that any problem with DSL will be recovered on the ARQ. Of course, we can decide to send the stream and ARQ over the DSL and have another backup of ARQ over the mobile line. That is perfectly reasonable and feasible. Next is the satellite backup. This is a very unique application that we developed, and it addresses the delivery and recovery of satellite feeds. In this example, we have an MCR sending a link through a RIST device, and a simple profile unidirectional stream is sent over the satellite to multiple destinations. We can then put RIST devices at the destination, and we can create a link of trickle packets going through, like a very low port ratio, or to do only ARQ. Any low packet loss on the receiver on top can be recovered using the light brown link. So 1% packet loss can easily be recovered with ARQ. But then we can also have a full outage. In this case, you can see a full outage of satellite. The receiver doesn't see anything. We can now recover that delivery. 100% packet loss can be recovered using the RIST. And when the satellite comes back, everything goes back to the satellite. So the IP delivery costs are dropping significantly. This reduces the operational costs and effectivity and tremendously improve the resilience of satellite delivery now with the C-band and 5G interferences or any other interferences that might happen. So we come to the end. Thank you for staying with me. My contact information is included. It's adi.rozenberg@videoflow.com. You can drop me an email for additional information. I urge you to join the RIST forum or the RIST activities in that fact. Thank you very much for your time.